We are still on straight lines, and in this lesson we are going to look at finding the equation of a straight line. So an overview of this lesson is, first we're just going to revise the standard form and also go through the general method of finding the straight line equation, and then also look at some practical examples of determining the equation, and then finally look at examples with a restricted domain. Now, whenever we are asked to find the straight line, what we're going to do is immediately write down your standard form for a straight line. And the reason being is, in an exam or a test, there's 4 different types of functions, and each of them has their own unique standard form. So they can ask you to sketch any of those. So the moment they ask a specific one, write that specific one's standard form down, then you know what you are working towards. So in this case, we have 2 values that we need to find. The first one is the gradient and the C value. So that immediately tells you also what to find, and then substitute back into the standard form. So first of all, the gradient. The gradient we already know quite well, and we also know that if I'm given a function on a Cartesian plane and it has 2 points, more specifically 2 coordinate points, what I do is I take those 2 points and I substitute it into my formula for the gradient. So the formula for the gradient is the change of y over the change of x. All right, so and that's basically it. That's how we find the gradient when we're given 2 points. All right, and then we're left with finding the C value, and the C value is the y-intercept. So in some cases, it's actually extremely easy to find the C value when we are given a graph and the graph actually goes through the y-intercept at a specific or given point. Then that immediately tells us that this is the C value right there. So, but in other instances, what if we're not given the y-intercept? What we do then is we substitute the gradient that we just found and another point that's also given into this formula over here. And this formula isn't, it's not really, it looks funny here, but it's actually something we already know. If we just take the x minus x1 and we place it underneath the change of y, this is just basically also the gradient formula. And what's nice about this formula is after you substitute it in the gradient and also the point, you can just simplify it and it works out immediately towards the equation of your straight line. All right, so this is then the summary of finding the equation of a straight line. So let's go ahead to the next section and then see how we apply that practically. Okay, so for example 1, it says determine the equation of the straight line through the points 1, minus 3, and negative 2 and 5. So first of all, we asked for the equation of the straight line, which then means we immediately write down the standard form of our straight line, which is y equals to mx plus c. And we know we have to find the m value and the c value. So the m value, we know the formula. Gradient is y2 minus y1 over x2 minus x1. And then what we can do is you can go ahead and directly just substitute it in. But what I like to do is to list them underneath each other. And in doing so, I just go and I say, okay, these are my x values, these are my y values. So I'm just going to say the top y minus the bottom y over the top x minus the bottom x. So I'm just going to say 5 minus negative 3 over negative 2 minus 1. All right, and then we just simplify. So this minus and minus becomes a plus, which then gives us 5 plus 3, which is 8, over minus 2 minus 1, which is minus 3. Right, so then that is our gradient right there. And then we can see that we aren't given the y-intercept. So that means we're going to need to use the formula y minus y1 is equal to the gradient times x minus x1. All right, and then we just basically substitute in the value. So we can basically substitute any of these two points in. So we just choose one. So I'm going to say y minus the y value negative 3 is equal to the gradient negative 8 over 3 x minus my x value is 1. And then I just simplify. Minus and minus is a plus, so y plus 3 is equal to, and then I, on this side, multiply into the bracket, so I have minus 8 over 3 x, and then minus and a minus is a plus 8 over 3. And final thing I need to do is take the 3 over and then just add the like terms. So y is equal to negative 8 over 3x plus 8 over 3 minus 3. And then this just gives me, so I'm just going to add my like terms over here. This has got a constant of x, so I can't add that. So you have negative 8 over 3x. This becomes minus 9 over 3, so this becomes negative 1 over 3. All right, so here we have then our standard form. So just to run through everything quickly again, we were asked to find the equation. We wrote down the standard form of the equation. Then we saw we needed to find the gradient and the c-intercept, or the c value. We found the gradient using this formula, substituting it in and simplifying. And then finally, we used this formula and substituted in a point and the gradient we found. And that led us to our final equation. Okay, so in this question, basically the same question, our data is just represented on a graph. So I'm going to go ahead and do the same thing. We are asked to find the equation, and we can see it's a straight line. So y equals to mx plus c. And then we need the gradient and the c value. So first of all, the gradient is equal to y2 minus y1 over x2 minus x1. Okay, so let's subtract top from bottom. So 2 minus negative 1, the y values, 2 minus negative 1, over 3 minus negative 3. Okay, and then we just simplify that. So this becomes 2 plus 1. That gives us 3, and 3 plus 3, the minus and minus becomes a plus, and that's 6, which then simplifies to an equivalent fraction of a half. Okay, so now finding the c value, it seems like it's halfway between 0 and 1. Although something very important you need to remember when you write when you're writing tests and exams, your functions are barely, if ever, drawn to scale. So we can never assume something because it looks like it. We have to, if it doesn't say so, then it isn't so. So if the graph, for example, went through 1, we could have said, okay, yes, our c value is 1, but it has no data there. It doesn't give us any information there. So we can't just assume that it's half. All right, so that means we have to go ahead and once again use this formula, gradient times x minus x1. So what I'm going to do is I'm going to substitute at 1 point. Let's just use that point. We can use any one. And then also the gradient that we calculated earlier. So we have y minus, my y value there is 2. My gradient is a half. And x minus the x value there is 3. And then we just simplify. Now, what I'm going to do is, because this is already like, we don't have to multiply anything out here, I'm going to multiply out this bracket, and then also in the same step, just take the 2 over to the other side. So I have y is equal to a half x minus 3 over 2 plus 2. So here I multiplied out the bracket and I got these two terms. And this plus 2 I got from taking the minus 2 over to the other side. And now we just add the like terms. So we have y is equal to a half x minus 3 over 2 plus 4 over 2 basically is a half. So here we have it. We have y is equal to half x plus a half. So it was a half, but once again, we still can't just assume that it was. Okay, now in this example, we see one of our special lines where if we look at all the points on the line, whatever point on the line, the y value is always 3. So when you have a horizontal line, your y value is always constant. And we can go through like the previous steps and write down the standard form, find the gradient. But what you'll find, if you do find the gradient, you'll calculate it as 0. It will come out as 0. And that will be the case always with horizontal lines. So we actually don't have to go through all that work. We can just say, if we see a horizontal line, we can immediately know it's y equals to wherever y goes through. So y equals to 3. If I, for example, just to give you another example, like if we have this line over here going through -1, the equation of this line will be y equals to -1. And also, something important, the x-axis, the equation of the x-axis is y equals to 0. Alright, so then, just to go further, this isn't really a function, but we can have a line that goes vertically through a point. And in that case, the x is constant. So for any point over here, it's always going to be 1 and something. 1 and 1, or 1 and 2, or 1 and 3. So in this case, the equation of this line will then be x is equal to, wherever x goes through, 1. And if we have a line through here, we have x is equal to -4. And what is the equation of the y-axis? The equation of the y-axis will then be x is equal to 0, because the x value is a constant 0. Okay, so that was then how we did it practically. Final section. In example 4, it says draw a sketch graph of y equals to fx equals to -x plus 4 with the domain of from -2 included to 3 excluded. Okay, so basically, don't let this confuse you, this part. They could have just given you the function like this. They just decided to write y equals to this equals to. Okay, so what we're going to do is we have our Cartesian plane, and we already know how to draw a function. In the previous video, there's one of 3 ways: dual intercept, gradient intercept, and the table method, or ordered pairs. Now, I'm not going to go into detail into drawing this actual graph, but if we should draw this graph just like a normal graph, it would look like this. Okay, but the difference between this graph is that it is restricted, meaning from -2 to 3. So the graph does not exist before -2, and it does not exist after 3. Now, how we're going to sketch that is another thing we have to pay attention to is these brackets. We can see that the first bracket is a square, and if it's a square bracket, we know that it includes -2. So the point -2 is also part of the graph. But if we look at the round bracket, it excludes 3, meaning the point at 3 is not part of the graph. So how to represent that? We're going to make a dot on 2, but a closed dot. That tells us that 2 is included, or -2 is included. And we make an open dot on 3, showing that 3 is not is not included. So after that, we just connect those two, or just draw a solid line, and then we erase. What I just forgot to say is you draw your original graph in pencil, then you do all these things, and then at the end you just erase that graph, and then you're left with the actual restricted graph. Okay, and then for B, what is the range? Now, in this case, this is our domain. Then the range is our y values. So remember to read your range from the bottom up. Now, we can write it in one of 2 ways. Remember, you've got your set builder notation and interval notation. So with set builder notation, we go from 1. 1 is less than y. and it's just less than because it's not included, and y is less than or equal to 6 because 6 is included. Okay, so that's the one way. Or the other way, we can say y is an element of from 1 to 6. So 1 is not included, meaning it's a round bracket, and 6 is included, so we have a closed square bracket. Right, then for example 5, what is the domain and range of the following graph? So this is basically the same as the previous one, where for the domain, we know that is our x values, and we can write it in one of two ways. So x starts at 0 and it goes up to 5. So I have from 0, and 0 is an open dot, so it's not included, so it's less than x. X is less than or equal to, since it's a closed dot, 5. Or I can write it as x is an element from 0 round bracket because it's not included, up to 5 being a square bracket because it is included. And then for the range, we have from -7 up to 4. So if I have -7 is less than y, only less than because it doesn't include -7, is less than or equal to my y value there, which is 4, or I can write it as y is an element from -7, open bracket, up to 5, closed bracket. So you can choose either of these, you don't have to use both. For domain, either this notation or that notation, and then same for the range. And then for the final example, what is the domain of the linear function? Y equals to 3x minus 4 if the range is from -5 inclusive up to 7 excluding 7. Alright, now if we look at the actual function, just to represent this graphically, just a very rough sketch of what this function might look like. We have one point from -5. We can see that it goes from -5 up to 7, and we have a point round about here, and this is a closed dot because it includes -5. Here it's an open dot because it does not include 7. So we basically need to find the range from this value up to that maximum value over there. And to find the y values, if our x values for this one, for example, is 7, to find our y value there, we're basically going to substitute our x value into our equation and find the y value, and we're going to do the same here for this -5 to find the y value there. So we can start off and say, okay, if x is equal to -5, what is my y value? Y is equal to 3 times by -5 minus 4. So this is -15 minus 4 is -19. So this is then -19. And then for x being equal to 7, we have y equals to 3 times 7 minus 4. So that's 21 minus 4 gives me 17. All right. So then I have 17 over here. And now I can see that my range goes from -19. So I can write it as -19 is less than or equal to, because it includes -19, y. Y is less than 17, but only less than because it does not include 17. Okay, so, or I can write it as y is an element from -19, including -19 up to 17, excluding 17. Okay, and that was then the last of the 3 sections.